For our final Laplace transform, we need to prove that the Laplace of sin bt e raised to negative 80 is equals to b over a plus s squared plus b squared. Let's start. Plus 0 to infinity sin bt e raised to negative 80 times e raised to negative st dt. We combine like terms and we have infinity sin b t e negative t times a plus s dt. Next is we use integral by parts. So our u is sin bt and our du is b cosine bt dt. Our dv is negative e raised to negative t a plus s dt, and our v as usual is negative 1 over a plus s times e raised to negative t times a plus s, and then we substitute it. So our u is sin bt all over times v is negative 1 over a plus s times e raised to negative t a plus s from limits to 0 to with a very large number minus integrals of negative 1 over a plus s times e raised to negative t a plus s, and our du is times b cosine bt dt. So by mentally solving this part of the equation, we can say this is 0 because e raised to a very large number is 0 and sin 0 is 0. So now we need to pull out the constant for this one, the equation, and our constant is b times negative 1 over a plus s times negative is positive. So b positive b over a plus s times the integral of what's left of this part of the equation is cosine bt times e is negative t a plus s dt. And again, we use integral by parts. So our u is cosine bt and our du is negative b sin bt dt. Our dv is e raised to negative t a plus s dt, and our b as usual is negative 1 over a plus s times e raised to negative t a plus s, and then we substitute again. Don't forget b over a plus s times our u is cosine bt all over negative a plus s times e is negative t a plus s from limit 0 to a with a very large number minus integrals of negative 1 over a plus s times e raised to negative t a plus s, and our du times negative b sin bt dt. And again, by mentally solving this, we have a substituted into this and raised and equated by e. We have 0, but cosine 0 is 1. So what's left is b over a plus s 1 over a plus s That's what's left of this equation. And now we pull out the constant. Our constant is negative b times negative 1 over a plus s times negative is negative b over a plus s. With integrals of what left is sine bt times e raised to negative t a plus s dt. And now we will equate it from our first equation, which is this one. So we have integrals of sine bt e raised to negative t times a plus s dt is equals to b all over, we multiply it now, b all over a plus s squared b minus b squared all over a plus s squared with the integrals sine bt e raised to negative t times a plus s dt. And then we will transpose this into this part of the equation, then pull out like terms. So we have 1 plus b squared all over a plus s squared integral sine bt e raised to negative t a plus s dt is equals to what's left of this part of the equation is b over a plus s squared. So we divide it by 1 plus b squared all over a plus s squared. Cancel this. So we have this part of the equation that says integral of sine bt e raised to negative t times a plus s represents as Laplace of sine bt e raised to negative at. So we can make this as Laplace of sine bt e raised to negative at is equals to b all over a plus s squared all over 1 plus b squared over a plus s squared. There. But we can still simplify this. So we have b all over a plus s squared all over, we simplify first the denominator, we have a plus s squared a plus s squared plus b squared. Now we multiply. We multiply b times a plus s squared, we have b times a plus s squared, and we multiply a plus s squared times a plus s squared plus b squared. We have a plus s squared times a plus s plus b squared. We can cancel. So our final answer is b a plus s squared plus b squared. And that is how we prove that the Laplace of sine bt e raised to negative at is equals to b over a plus s squared plus b squared.